Bismillahirrahmanirrahim. Assalamu alaikum. Today I welcome you ninth lecture of lecture series in Symbolic Math Toolbox in MATLAB. Today we are in this lecture we try to solve this how to calculate the Fourier series coefficient in MATLAB. Before going to the MATLAB, I just want to revise some concept of Fourier series and why we calculate the Fourier series. Let's start and then go to the MATLAB. How can we implement? Mathematical transform. In mathematical transform, we usually transform signal or function interchangeably. In engineering, we call signal. In mathematics, we call function from one domain to, or normally time domain, or another domain, frequency domain. What is time domain? I already explained what is time domain and what is frequency domain in my previous lecture of spectrum. If you didn't see my lecture, I put description link in my description, so you can see and go and see that lecture. What is time domain? Time domain refer to the analysis of mathematical function or signal with respect to time. In simple word, time domain function mean if the independent variable of that function is time, then we call this function time domain representation. In time domain representation, the graph shows like the x-axis of the signal is with respect to is time. The independent variables always draw on the x-axis. So in the time domain signal, we have time on the x-axis and we have amplitude at the y-axis. And what is frequency domain? The frequency domain refer to the analysis of mathematical function or physical signal with respect to frequency. In simple word, the function independent variable is frequency, then call frequency domain function. Whereas the frequency domain graph shows how much of signal lies with each frequency band over the range of frequencies. And normally we call this representation is called spectrum. Why we need frequency domain representation? The answer is very simple: to get the extra information that is not available in the time domain signal. And what is kind of information we have in the signal? That is basically how many frequency component present in the signal and what are the amplitude and phase of each frequency component. These are the information we want to know about our signal that is not available in the time domain graphical representation. So we need to transform our function in the frequency domain, and using this plot of spectrum, we can see each frequency component and having what they have amplitude and phase. So for the transformation, we have normally used Fourier. We have Fourier series and Fourier transform. Fourier series normally we apply on the periodic signal, and the spectrum after applying the Fourier series is the discrete spectrum. And the Fourier transform we apply on the aperiodic signal, periodic function or signal. The spectrum after applying the Fourier transform is normally usually continuous spectrum. So why it is continuous, why it is discrete, and how this is I try to have another lecture on the Fourier series and Fourier transform and mathematical description of how we get the formula of the Fourier series and Fourier transform, why it is continuous spectrum, why it is discrete spectrum. I try to make extra video lecture on the Fourier. So now going back to the Fourier, in this lecture we try to focus our attention on the Fourier series. So what is Fourier series? According to the Fourier series is a way of representing a periodic function as a possibly infinite sum of sine and cosine function. Or a Fourier series a way of representing a signal, a linear combination of finite or maybe infinite sum of n sine and cosine function having different amplitude, phase and frequency. According to the Fourier, we can represent the statement of Fourier series. Basically, according to the Fourier, we can represent any signal a finite or maybe infinite sum of sinusoidal waveform having different amplitude, phase, and frequency. If they are periodic, then they are harmonically related. What do you mean by harmonically? They are integer multiple of fundamental frequency. So what is fundamental frequency? I'll explain in my next lecture when I on the Fourier Transform or Fourier series. Okay, so this is the statement, and you can see on the graph and how we calculate the Fourier series coefficient. Formula is very simple. Fourier series coefficient AK is equal to 1 over T naught 0 to T naught x of t ej 2 pi k over T naught t into dt, and for the DC component, that is A naught is equal to 1 over T naught 0 to T naught x of t dt. And what is AK? AK is basically complex amplitude. A is the complex, A denote the complex amplitude, and K is basically representing the harmonic number. What is harmonic? And harmonic is basically integer multiple of second fundamental frequency. Fundamental frequency is the lowest frequency. For example, if we have fundamental frequency is 2, then its first, second harmonic is 4, second multiple, third multiple is 6. So K representing the harmonic number. Normally, if we have periodic, because we are talking about the Fourier series, and Fourier series apply on a periodic signal, and for the periodic signal, all frequency component are integer multiple of fundamental frequency. So that is basically for the Fourier series formula. How we get this formula, I already explained. I already told you I'll explain in my Fourier series lecture. So let's start our example. How we can calculate the coefficient using the MATLAB. Here we have a square wave, 50% duty cycle square wave. 50% duty cycle mean this square wave is on in mean 1 for the half time period 0 to T naught, and 0 is for the T naught half time period from T naught by 2 to T naught. And the mathematical formula piecewise expression of this waveform is x of t is equal to 1 from 0 to T naught by 2 and 0 to T naught by 2 to T naught. And these are the formula because this function is 1 from 0 half of the time period and 0, and we don't need to integrate from the half of the time period. So the formula of AK complex amplitude is 1 over T naught 0 to T naught 1 ej 2 pi k over T naught t dt, and for A naught that is 1 over T naught 0 to T naught by 2, that is 1 into dt. And after calculating the Fourier series coefficient, we have this expression. Now we are going to calculate this on MATLAB. Let's start and share you. I share you MATLAB screen with you, and that is my MATLAB screen. So first I CLC clear all variables from the screen. CLC again, sims sims variable when I need T naught, T and K, that I need variables. So first of all I initialize basis function. My basis function of Fourier BAS basis function, that is ej 2 pi k over T naught t. So that is my basis function. Easy to calculate the Fourier transform. And now I am going to calculate A naught, that is equal to 1 over T naught. If we can see the formula, I'll share your screen, and here we have a formula. A naught is equal to 1 over T naught 0 to T naught by 2 1 into dt. So again go back to the MATLAB. 1 over T naught into int integral 1 into T into your limits 0 to comma T naught by 2, and we have a DC component 1 by 2, and you can see here we have a DC component. Here is my slide. Here, we have a DC component A naught 1 by 2. So that is now again go back to the MATLAB. That is basically DC component. Now I am going to calculate the coefficient AK, that is equal to again 1 over T naught. I simply change AK 1 over T naught 1 into B basis function BASI. Basis again limits will remain same. I don't need to change the limit from 0 to T naught. Formula is same, and here we have a and pretty AK, and you have this expression pi Ki minus I over Pk. No, that is basically complex amplitude expression. Now what I need to do, calculate the value of complex amplitudes from minus 10. I'm going to plot my spectrum from minus 10 to 10. So that's why I'm going to find the value of complex amplitude from minus 10 to 1. A 1, I simply substitute the value of a k value in a k complex amplitude from minus 10 to minus 1, and again SP2, again I have this, and that we have value. Now I want to AKD, that is basically SP1 A naught. I simply change the symbolic variable values into double, so we can plot a spectrum. And here we have these values, and STEM AKD STEM, that is ABS, and we have this spectrum. Sorry, I think there is some mistake. Sorry, yes, 2, and here we have a spectrum of. The spectrum shows 0. We have amplitude 1 by 2, 0 2 pi k, and this complex amplitude is 0 for the even harmonics and non-zero for odd harmonics, as you can see in the slide. This piece AK is 1 over j pi for k is equal to 1, 3, 5, 7, and so on, and 0 for the 2, 4, 6, and so on. It means this complex amplitude is 0 for the even harmonics and non-zero for the odd harmonic, and 1 by 2 at k is equal to 0. If you can see the spectrum show the same thing, that is 0 to at 0 this value is 1 by 2, and this spectrum is 0 for the even values 2, 4, 6, 8, and 10, and non-zero for the 1, 3, 5, and this is the spectrum of the square wave. So that is our first example. Okay, and now I am going to for the next example, if we have a triangular waveform and we want to plot the spectrum. So for the triangular waveform, again we have x of t is equal to 2t over t naught from 0 to t naught by 2, and 2t naught minus t over t naught from t naught by 2 to t naught. Again we have a formula for a naught and ak. Now let's start to calculate this. F1, simply I define F1. F2 basically is second function for the triangular waveform. This is basically from this F1 is 2t over t naught, and F2 is 2t naught minus t over t naught. That is basically F1 and F2. So again, now I'm going to calculate the A naught. What we have, 1 over t naught. Let me share. this screen with you. A naught is equal to 1 over t naught from integral f1. This first function is with respect to time 0 to t naught by 2, and then plus f2 function 2 with respect to time t naught by 2 to t naught. I simply press the enter key and find the a naught DC conversion. That is basically gain 1 by 2, and you can verify this from the slide. Again, that is basically 1 by 2 at k is equal to 0. Now I want to calculate AK. Again, what we need to do is that basically we change the A naught. What I need to do, simply change K. Here we have F1 multiplied by PASI, and again for the F2 BASI. Just need to simply change the value of and simple press enter key. Here we have the complex amplitude after integrating xak pretty ak. Again we have this function. Now sp, I'm going to calculate the function sp3. We have ak, again this minus 10 to this, and sp4, let's suppose this, and akd, again sp3 and sp4 from 10 to this to plot the spectrum, and simply enter. And again stem minus 10 to 10, we want to plot the spectrum from minus 10th harmonic to 10th akd get spectrum. And if I simply press the enter key, you will find the spectrum of the signal triangle waveform at k is equal to 0, and that is 1 by 2, and k1 3, and this function is again non-zero for the odd harmonic and 0 for the even harmonic. So that is from the today lecture, as I show you in my slide, ak this expression, and we calculate the spectrum as it is. We just need to make it very simple to avoid any mistake. Just simply define everything with different variables, so you can easily input in the expression and avoid any error. So today, this is from the today, and I hope you like my today's video. Kindly share and subscribe my channel, and like and comment if you can. And if you need any other my help, any other any problem, you can share in my comments. Allah Hafiz.